Yes, friends, so welcome to lecture number 4 of Maths Optional for UPSC CSE. Let me see if the recording has started or not. Yes, so the recording has started. Now, up to the lecture number 3, we had learned some 10 properties of skew symmetric matrix, if I am not wrong. So, we will continue from the orthogonal matrix portion. So, put the heading orthogonal matrix. Orthogonal matrix. So orthogonal, as the name suggests, there must be something called as 90-degree or something like that. Okay. So orthogonality always means like that only. So 90-degree means over here the relationship between the original matrix and the transpose is being taken. Okay. So a square matrix, a square matrix A equal to A ij is called orthogonal matrix. Orthogonal matrix if and only if. If means if and only if. That means necessary and sufficient condition. This condition is necessary also, means this condition must be satisfied, and this condition solely is sufficient. Okay, no other condition is required. If means this condition is this condition alone is sufficient. This condition is compulsory and alone is sufficient to. Okay, so condition is compulsory and alone is sufficient to. So IWF if A transpose is equal to identity matrix is equal to A transpose A. Okay, now I had told you the meaning of transpose in the previous classes. If you haven't watched the previous classes, then the link is there in the description. You will get the link in the description. You can click on that link and you can watch from the first class. Okay. So I had told you, right, because suppose let us take a simple example, 1 2 3 and 4. So how is the transpose found out? The transpose is found out by interchanging the rows and columns. Okay, so basically this row will become the first column and this second row will become the second column. Okay, so you can write it like this, that this 1 comma 2 will come over here and this 3 comma 4 will come over here. Okay, so the rows will become columns. Okay, so that is the meaning of transpose. So suppose if A multiplied by A transpose is equal to I. Okay, so yeah, if this condition is satisfied, that multiplication of a matrix with its transpose and multiplication of a transpose by a matrix, okay, means multiplication of a matrix by a transpose or multiplication of a transpose by a matrix, by the original matrix, if it comes out to be equal to I, then the square matrix is called as orthogonal matrix. Okay, so square matrix A will be called as orthogonal matrix. You can write m cross n over here. Okay, so this is the thing. So properties of orthogonal matrix, now we will move on towards that. Properties of orthogonal matrix. Properties of orthogonal matrix. Property number 1. If, okay, again necessary and sufficient condition is coming. If A is an orthogonal matrix, then determinant of A will be equal to either plus 1 or minus 1. Okay, so I will write plus minus 1. So we can say that determinant of A, okay, the determinant of A will be equal to plus or minus 1 only if and only and only if the matrix A is a orthogonal matrix. Okay, if and only if matrix A is an orthogonal matrix, only then the determinant value will be either equal to plus 1 or it will be equal to minus 1. Okay, so and other thing is that A will be a non-singular matrix. What does it mean by non-singular matrix? Let me write over here. And A is non-singular matrix, and A is non-singular matrix. Now A is non-singular matrix simply means that the determinant value is not equal to 0. This simply means that the determinant of A value is not equal to 0. This is what is meant by non-singular, because for a singular matrix the determinant of a singular matrix is equal to 0. So let me write over here the determinant of a singular matrix is, okay, determinant of a singular matrix is 0. So A is a non-singular matrix. Now let us prove it. Okay, let us prove it. So proof, let us prove it. Let A be any orthogonal matrix. Let A be any orthogonal matrix. Let A be any orthogonal matrix. Then what is there? A transpose is equal to I. Right now, just a moments ago, we had proved that if A is a orthogonal matrix, why this is there? Because A is a orthogonal matrix. That's why A transpose is equal to I. Just some moments ago we had proved this, right? Not proved, but stated this theorem. Okay, that if A is a orthogonal matrix, then by definition of orthogonal matrix, this is the condition which an orthogonal matrix must satisfy. This condition, okay, this is the condition which an orthogonal matrix must satisfy, right? So by definition of orthogonal matrix, you can write over here by definition of orthogonal matrix. Okay, so this is by definition of by definition of orthogonal matrix. This is the thing which you got. then you will take determinant on both the side. Okay, take determinant operation on both the sides. Then as soon as you take the determinant operation on both the sides, what do you get? So therefore you will get determinant A A transpose, that will come out to be equal to determinant of I. Okay, determinant of I. Then by the property of determinant, this determinant of I will be equal to 1. This you know already. And apply the distributivity property over here. So by applying the distributivity property, you will get something of this kind. Okay. So determinant of A transpose means determinant of two matrices multiplied together, original matrix and its transpose multiplied together, original matrix and its transpose multiplied together. When you take its determinant, it is equal to the product of individual determinants. It is equal to the product of individual determinants. Okay, so you took the product of individual determinants. So I will write the reason over here why I took it like that, because determinant of AB, what is it equal to? It is equal to determinant of A multiplied by determinant of B. Okay, so this is the reason why we took like that. So in the place of B there is A transpose. At the place of B, what is there? A transpose is there. At the place of A, what is there? A is there. Okay, at the place of A is there, but at the place of B, A transpose is there over here. Okay, over here I am saying, over here. Okay, so this is the thing. And now you must be knowing, let me write this once again. Okay, so what we have got? We have got determinant A multiplied by determinant A transpose. We have got this equal to 1. Now you know this very well, that determinant of A transpose is equal to determinant of A. Do you know this? You must know this. This is a 12th class concept. Okay, if you were in CBSE class 12th in case, then you must have been, it must have been in your syllabus. Or even if you were in state board in the 12th class, still you must have learned this concept in your what we can say BSc. Okay, you must have learned this concept in your BSc. Okay, that determinant of A transpose is equal to determinant of A, BSc or MSc whatever, but you must have learnt it. Okay, somewhere in your syllabus. So determinant of A transpose is equal to determinant of A. So clearly I can substitute this value over there, and finally what will I get? Determinant of A multiplied by determinant of A will be equal to your 1. Okay, so these two things multiplied together yields you 1. So now if you simply uh, do like this. Okay, now this, consider this whole thing to be a single quantity. Okay, this is a single quantity, right? Let me mark over here. This is a single quantity in itself. This is a single quantity in itself. Okay, so as both of those are single quantities, so I can write like this over here. I can write like this: determinant of A whole square, okay, is equal to 1. Okay, so never do the mistake in the exam like this, that you are writing something of this kind, determinant square A square. It is not like that, because this is whole one number, okay. This in itself is a whole one entity, single entity. Determinant a is a single entity, determinant a is a single entity, okay. So determinant is square a square, you can't write like this, okay. This is completely wrong. So never make this mistake in the examination. So determinant a whole square is equal to 1. No, I know that you won't make that mistake, such a silly mistake. I know you won't make, but still some students might be very what we can say poor. So for those students, I am writing all the steps. So taking square root, okay, taking square root, taking square root on both the sides. So as soon as you take the square roots on both the sides, what do you get? You get something of this kind, okay. So you now know this, that determinant of a is equal to plus minus 1. Now I had told you that when, let me write over here, when determinant of a is equal to 0, that implies that matrix A is a singular, okay, singular matrix, okay. And when determinant of A is not equal to 0, that implies matrix A is a non singular matrix, okay. So clearly you can see this thing, that determinant A not equal to 0 condition is being satisfied over here. Determinant A has come out to be equal to plus minus 1. Determinant A has come out to be equal to plus minus 1. So clearly it is not equal to 0, okay. So clearly this whole thing is not equal to 0. So what is your, so that's why that implies that your matrix A, the matrix A is non-singular, okay. So this is the thing which you have got. Now let us move on towards the second property. What does the second property say? Let me write over here, okay. Let me change the color also, okay. If A is an orthogonal matrix, write over here, if A is an orthogonal, then A transpose is also orthogonal matrix. So if A is a orthogonal matrix, then A transpose is also orthogonal matrix, okay. So for, in order to explain that over here, we will do the explanation of this, I mean proof of this. So let A be an orthogonal matrix. So it is the given condition. The condition is given to you initially if A is an orthogonal matrix. So after then, whatever is written after then, okay, the things which are written after then, the things which have been written after then, those will be, we have to prove those, okay. So let me write over here, okay, before then, Okay, before then whatever is written, it is the given condition. After then whatever is there, okay, after then whatever is written, that is the to prove condition. Okay, so the meaning of this is very simple. Okay, if, what does it mean by if means agar. Okay, if means agar. What does it mean by if means agar. Agar. Okay, and what is meant by then means to. Okay, so what does it mean? अगर अगर ये अगर ये अगर ये तो ये, so obviously this is given one, this is given one, and this is to be proven, this is to be proven. Okay, so let's start the proof. Let's start the proof of this. Let A be an orthogonal matrix. Let A be an orthogonal matrix. Okay, then what will happen? I had already told you by definition of orthogonal matrix what will happen. A transpose will come out to be equal to I, and that will come out to be equal to A transpose A. This is by the definition of orthogonal matrix. Okay, then what will we do? We will take transpose on both the sides. Take, this is by definition, by the way, by definition. By definition of what? By definition of orthogonal matrix. By definition of orthogonal matrix. Okay, so take transpose on both the sides, on both, okay, on both the sides. So you take the transpose on both the sides, so what will happen? A transpose, we will take its transpose. Okay, then I, we will take its transpose, then A transpose A, we will take its transpose, right? Then I had told you one property of transpose. Which property of transpose did I tell you? I had told you one property of transpose, that A, B, okay, let me erase, something wrong has been written. Okay, so A, B transpose. Okay, so what is it equal to? B transpose A transpose. It is equal to like this, right? So you do like this: A transpose transpose A transpose. Okay, by this definition, by this property, not definition, property, by this property. Okay, so similarly I transpose, Now the transpose of a identity matrix is identity only. So again the same property we will apply. A transpose, A transpose, transpose, right? So this is the thing. Now if you look at this expression very carefully, look at this expression very carefully. Which expression? Which I am highlighting with the laser. This expression, this expression, and I am going to write it on the next screen also. Okay, this expression, you look at this expression very carefully, and let me write this expression on the next page also. Okay, so let us write this expression on the next page also. So A transpose, transpose, A transpose is equal to I is equal to A transpose, A transpose, transpose. Okay, now a person, a careless person, what a careless person will do? A careless person will use this property, A transpose transpose is equal to A, and he will use this property and will convert this into A transpose is equal to I is equal to A transpose A. He will convert it into this. But this is a wrong thing. This is a wrong thing. Why? Because look at the property. What is to be proved to you? If you look at the property, we have to prove that A transpose is also orthogonal. What we have to prove? A transpose is also orthogonal matrix. We have to prove this. Okay. So we will only prove up to the statement which we require. But if you look at this statement does not prove that A transpose is a orthogonal matrix. But if you look at the previous step, this one, this step proves that A transpose is an orthogonal matrix. You look at this step clearly proves that A transpose is an orthogonal matrix. Okay. So erase all these things. Do not use the property A transpose is equal to A over here, because it is not going to yield you anything. Okay, it is not going to benefit you. So what will benefit you? Keeping this expression as it is will benefit you. Okay, so by definition of orthogonal matrix, you know this very well, that when A transpose, okay, when A transpose is equal to I is equal to A transpose A is there. Okay, so we call that to be an orthogonal matrix, right? By the definition, we call it an orthogonal matrix. Now substitute A is equal to A transpose here. Okay, so after you substitute A is equal to A transpose over here, what do you get? You get something of this kind. Okay, okay, you get something of this kind. So what does this mean? Okay, and this is identical to this is identical to this. Okay, so when A transpose will be orthogonal, okay, when, what does this imply? This implies that A transpose is orthogonal. Okay, if this statement implies that A is an orthogonal matrix, A is an orthogonal matrix, if this statement implies that A is orthogonal matrix, then this statement will imply that A transpose is orthogonal matrix, because you have just substituted A with A transpose. Okay, so A transpose is orthogonal. This is what is meant by this. Okay, so these and these are identical. So after proving all this, okay, after proving all this, you came up to here. So what inference will you draw? Okay, what inference will you draw? Just cut this. Okay, this is for explanation, this is for explanation. So the inference of this, what will be the inference of this? So the inference is very clear. Okay. So inference is A transpose is orthogonal matrix. This is the inference which you can draw. Okay. So let me just come back in a while. Okay.